Welcome back, fellow math nerds. Let's learn about sequences. Sequences of numbers can be defined in two basic ways. We can be really formal about it, or we can be informal about it. The formal way is that sequences are actually defined in terms of functions, whose domain is the natural numbers, and we list them out in the order of their inputs. But we usually use subscripts. Instead of writing f of 0, we write f sub 0, and so forth. Informally, we just list out numbers, okay? And that's really how we're going to think of them. They're just lists of numbers. Compared to sets, however, they do come in a specific order. There's f sub 0 and then f sub 1, and that doesn't mean f sub 0 has to be bigger or smaller. In fact, they can go back and forth. But I need to preserve the notion of which one came first and second and so forth. Our notation is that we use these braces, okay, to denote a set of things, but we then indicate a starting index and a finishing index. And for us, sequences have to contain infinitely many elements, so this finishing index is always going to be infinity. We can, however, change that beginning subscript. So if I say, for example, f sub n equals 4 to infinity, I start at 4. So I start with f sub 4, f sub 5, f sub 6. In practice, we're pretty much always going to start either at 0 or at 1. Every once in a while, it's going to be inconvenient to start at 0, but it's not a big deal. A lot of sequences we work with are defined algebraically. We have some sort of equation. Like I might say x sub n must be equal to 3n plus 2. So x sub 0 is 3 times 0 plus 2. X sub 1 is 3 times 1 plus 2, and so forth and so forth. Sequences can also be defined recursively. Like you might say, x sub 0 is 0 and x sub 1 is 1. After that point, x sub n plus 2 is the sum of the previous two entries. So to get x sub 2, you do x0 plus x1. To get x sub 3, you do x1 plus x2, and so forth and so forth. It's kind of expected that students at this point have worked with sequences, and this sort of notation is not terribly onerous, and you might recognize this as the Fibonacci sequence. However you can possibly list out numbers, however, if it's not algebraically defined and if you don't have a nice recursive formula, it's still a list of numbers, it's still a sequence. So don't think that a sequence has to have some sort of formula behind it. Any way that you could possibly list out numbers is a sequence. And what happens if a sequence isn't given by something explicit? Well, it can be very difficult to talk about, and it can be very difficult to prove stuff about, but it doesn't mean it's not a sequence. Now, there's a lot of definitions we can attach to sequences. So gird yourself. I'm going to take a deep breath, charge through. Here we go. So a sequence is called monotone increasing or strictly increasing, respectively, if one term is bigger than or equal to the previous one, that's monotone increasing, or strictly bigger than the previous one, that's strictly increasing. Monotone decreasing means every term is less than or equal to the one before it, and strictly decreasing means every term is strictly smaller than the one that came before it. It's monotone if it is either monotone increasing or decreasing either way. Oh, I couldn't get through it in one breath. A sequence is bounded above if the set of its values is bounded above. We already have a definition for a set to be bounded above. Just apply that definition to the set of values. Okay, we could also call it unbounded above if the set of values is not bounded above. We can call it bounded below if its set of values is bounded below, or unbounded below if it's not. And we can call a sequence bounded if the set of values is bounded, or unbounded if not. That is a lot of definitions, okay? There's 6 of them, and some of them kind of came in 2 parts. But they are all pretty straightforward, okay? Monotone just means a consistent inequality, and then either increasing or decreasing is pretty straightforward to figure out. Increasing means the terms are getting bigger. Decreasing means they're getting smaller. And we distinguish between, are we allowing equality, that's monotone, or not, that's a strict monotone. And just like bounded above and below, I mean, that just comes right from the definition of sets. If it's monotone in either direction, we can call it monotone. So let's take a look at a couple kind of examples of all of these things. So we can have, this sequence is going to be monotone increasing and bounded above. 1, 1.1, 1.11, 1.111, 1.1111, etc. Notice that every term gets bigger from one to the next. So it's not even just monotone increasing, it's actually strictly increasing. And it's bounded above because these are all going to be less than or equal to, I don't know, 57 or 56 even. So I can construct a strictly increasing bounded above sequence. Okay? I can also construct something that is bounded in both sides, but not monotone. Like this, 1 minus 1, 1 minus 1, 1 minus 1. It's definitely bounded. It's bounded above by 6 and bounded below by negative 11. Okay, more obviously it's bounded above by 1 and bounded below by minus 1. It's also not monotone. Here, I went from 1 to minus 1, that went down, but then minus 1 to 1 went up, and then down, and then up. It's not consistent about whether it's increasing or decreasing. It is not a monotone sequence, but it is bounded. Okay. You could also do something that is not bounded and not monotone. Like 1, negative 2, 3, negative 4, 5, negative 6, and so forth. Definitely not bounded either above or below, but also not monotone because it does this same thing the other one did of going back and forth between getting larger and then smaller, and then larger and then smaller. You can have a sequence that is not monotone but is bounded. You can have a sequence that is bounded above and monotone decreasing. You can have a sequence that is monotone increasing and monotone decreasing. Okay, so you can combine these sequence definitions in many ways. Here is an example of a fairly unusual sequence. Let's start by defining some sets. For each positive integer, I define f sub n to be all the rational numbers whose denominator is n, but notice the numerator goes from 0 to n, which means the number p over n goes from 0 to 1. So this is rational numbers in between 0 and 1 with a fixed denominator. So what is f sub 2? It's all rational numbers in between 0 and 1, whose denominator is 2. 0 over 2, 1 over 2, and 2 over 2. F sub 3 is 0 over 3, 1 over 3, 2 over 3, 3 over 3, and so forth. I'm going to define a sequence in the following way. First, list out all the elements of f1 in increasing order. Then when you're done with that, list out the elements of f2 in increasing order. And then when you're done with that, list out the elements of f3 in increasing order, and keep going. So here is 0, here is 1. First, what is f1? It was 0 over 1, 1 over 1. What is f2? Let's actually color code these. f2 was 0 over 2, 1 over 2, 2 over 2. Then, what about f3? 0 over 3, 1 over 3, I'll do one more after this, 2 over 3 and 3 over 3. And then finally, let's take a look at f sub 4. 0 over 4, 1 over 4, 2 over 4, and 3 over 4, and 4 over 4. So here's what I do to make my sequence. I list out elements of f1, 0, 1. Then I list out elements of f2, 0, 1 half, 1. Then I list out elements of f3, 0, 1/3, 2/3, sorry, this 2 didn't come out quite right, comma 1. Then I list out all the elements of f sub 4, 0, 1/4, 1 half, 3/4, 1. And I keep going. Okay, so here's how I'm making my sequence. I'm just going to keep doing this procedure. Once I exhaust all the rational numbers of a given denominator between 0 and 1, I move on to the next one. So here's what we end up with. Okay, here I haven't simplified them, that's fine. This sequence is bounded but not monotone, and furthermore, it contains every rational number in between 0 and 1 infinitely many times. There are infinitely many rational numbers in between 0 and 1, and they're all in there infinitely many times. So, by construction, every fn is between 0 and 1, so every element of the sequence is in between 0 and 1. The sequence is definitely bounded. Bounded above by 1, bounded below by 0. The way we did this is we listed out fn going from 0 over n to n over n. And since every n is finite, there's only finitely many elements in fn, which means we can always proceed to the next one. You have to be really careful when you use the word, once you're done with that, then do that. Because what if you have infinitely many things to do? So what I couldn't do, for example, is say list out all the integers and then list out all of the rationals or something like that. Because I can never finish listing all of the integers, I can't possibly say first list out the integers and then. But since the fn's are finite, I can say list out f1 and then list out f2 and then list out f3. But I'm not going to say, for example, list out all the fn's and then do something. Since there's infinitely many fn's, I would never be able to finish. Be very careful about using the phrase and then. But here, fn's are finite, so we can always move on to the next one. Each fn has several terms increasing. For example, f sub 5 is going to be 0 over 5, 1 over 5, 2 over 5, 3 over 5, 4 over 5, 5 over 5. I increase along the way. Once fn is exhausted, however, I have ended at 1 and then I go back to 0. So I do a bunch of increasing, but I'm always going to have some decreasing later on, which means it's not monotone in either direction. It's got some increasing terms and some decreasing terms over and over and over again. So the sequence is neither increasing nor decreasing. Okay, we did already show it's bounded. The only other claim is that every rational number appears infinitely many times. But any rational number p over q will eventually appear. Okay, once I get to f sub q, I'm going to have p over q. But then when I do f sub 2q, I'm going to have 2p over 2q. I didn't say anything about only taking simplified rational numbers. So even when we only did a couple terms earlier, we had, for example, 1/2, and then we had 2/4. More to the point, we had 0 over 1, and 0 over 2, and 0 over 3, and 0 over 4, and so forth. As soon as you see a number once, you're going to see it infinitely many times. But every rational number in between 0 and 1 will eventually belong to one of these things, and as soon as it belongs to one of them, it must belong to infinitely many. So this is a very unusual sequence. Construct a bunch of things given here, some other sample problems about proving properties of sequences. All right, again, hopefully you paused and worked through these things. Now, one thing that pops up if you did all these problems is that the rationals, because there's countably many of them, that means I can list them out. Since I can put them in a bijective correspondence to the natural numbers, I can define my sequence that way, f of 0, comma f of 1, comma f of 2, and so forth. So I can list out all the rational numbers. The rational numbers are ordered, okay? Any two rational numbers, one is bigger than the other, or they were the same number. But I can't list out the rational numbers in order. There's infinitely many of them, countably many, and they have an order to them. So I can list them out, and they have an order, but I cannot list them in order. It sounds weird, but it is absolutely true. If you thought you could list the rationals in order, what you'd have to do is say, well, what comes after 0? The next rational number? There isn't such a thing. Okay? In between any two rational numbers, we're going to find infinitely many other ones. You can't possibly list them in order. Now we can take a lot of the definitions we've just done for sequences of numbers and apply it to a sequence of sets. So now my a sub 0, a sub 1 are not just numbers, they are subsets of the reals, but we can still make a sequence out of them. Okay, so now instead of everything in the sequence being a number, everything in the sequence is a set. It's called monotone increasing or strictly increasing, okay, if moving from one term to the next, we have this subset relationship. Notice that a sub n plus 1 contains more points. A sub n is a subset of it. That's called an increasing sequence, if you are always adding points. Notice this has nothing to do with making bigger numbers, just adding more elements to the set. And if I want it to be strictly increasing, we just don't allow equality at any stage. Decreasing if the set containment goes in the other way. Monotone if it is either increasing or decreasing. Bounded above if these unions are bounded above or below. Bounded if the union is bounded. And in the context of sequences of sets, monotone is not very commonly heard. You talk about sequences of sets being nested if you have these containment operations. Either way, if it's an increasing sequence or a decreasing sequence of sets, both of them could be called nested. Like birds. So try to do a couple problems related to sequences of sets. Now these examples here were designed to free you from the notion that sequences of sets are terribly related to sequences of numbers. Okay, so you can have unbounded sets whose intersection is empty, things like that. So don't conflate what you know about sequences of numbers to also automatically apply to sequences of sets. The notions are related, but not exactly the same. That's going to finish it up this time. So please take a rest, come on back, refresh yourself, and we're going to keep talking about the structure of the real numbers.